Hello and welcome, dear listener, to the Sleepy Theorist. I'm so glad you're here. As you settle in, perhaps wrapped in your favorite blanket, the world quieting around you, the soft rhythm of your breath slowing with each moment, let your thoughts drift downward, not into dreams just yet, but into the cool, quiet world beneath your feet. Tonight, we're taking a journey not through the stars or the skies, but deep into the earth itself. Beneath the sidewalks and forests, under deserts and oceans, lie rivers that know I can see vast, flowing networks of groundwater that have shaped our world for millions of years. These are the hidden rivers, silent, secretive, powerful. They slip through sand and stone, through gravel and clay, quietly nourishing forests, filling wells, and even influencing the rise and fall of civilizations. You may not hear them, you may never see them, but right now, even as you lie still, they are flowing beneath you, like your own bloodstream, out of sight. But vital groundwater is Earth's slow, pulsing breath, shaping life in ways we often forget to notice. And tonight, we'll explore its story together, gently, unhurriedly, like water moving through soft layers of soil. Before we begin, if this gentle dive into science brings you peace, I'd be grateful if you gave this video a like or subscribed to the channel. It helps more sleepy minds find their way here. And if you're listening from somewhere special or it's a curious time where you are, leave a comment. I always love seeing where this quiet little community stretches to. One more thing, just before we begin. This video is for educational and relaxing purposes only. It is not intended to offer professional advice of any kind. Now, take a deep, calm breath in and let it out slowly. With that, let us begin the story of the Earth's hidden rivers, our slow, underground symphony that has been playing beneath us all along. Somewhere far above you, a soft rain falls. It might be pattering against leaves in a quiet forest, slipping down the tiled roof of a cottage, or gently collecting in shallow puddles on a city street. From your window, it looks like nothing more than droplets on glass, harmless, ordinary. But in truth, something profound has just begun. This is the beginning of groundwater's story. Not loud or hurried like rivers or oceans, not dramatic like thunder or storms. This story is patient, quiet, and very, very slow when a raindrop lands on the ground. It has choices. Some evaporate quickly, lifted back into the sky by the sun's warmth. Others get caught by leaves or roll away into nearby streams. But a special few take a different path downward. These droplets seep into the soil, soaking through roots and worm tunnels, through grains of sand and flakes of old stone. The soil drinks it ingridily at first, and the water begins its descent, guided only by gravity and time. This journey is called infiltration, and it's the very first step in how groundwater is born. Now, the earth is made of layers, a giant, rocky sponge. Some layers, like clay, are dense and heavy, and they hold water tightly. Others, like sand and gravel, are more welcoming, letting water slip between their particles with ease. As water moves downward, it enters these deeper spaces, the unsaturated zone, where air and water still mingle in the tiny gaps between grains. But if the rain continues, slowly, persistently, a point is reached where every crevice below becomes full. No more air, just water. This is the saturated zone, and the top of it is called the water table. It sounds like something out of a storybook, a table of water beneath the land, and in some ways, it is. It rises and falls with the seasons, like the breath of the earth. It can lie just a few feet beneath your feet in a marshy meadow, or hundreds of meters deep below the dry, cracked ground of a desert. And when water finds a home here in rock or sediment that can hold and carry, it freely enters something called an aquifer. Aquifers are nature's secret reservoirs. They do not look like underground lakes. There are no underwater caves or swimming spaces down there. Instead, aquifers are made of rock, porous, broken, full of tiny spaces holding water the way a sponge does. This water is not still. It moves, slowly, steadily, drawn by gravity from places of higher elevation to lower ones. Some aquifers lie beneath cities, quietly supplying drinking water to millions. Others sit under farms, feeding crops and animals through hidden pipes and pumps. Some have been undisturbed for centuries, their waters ancient and untouched, flowing so slowly they are measured in inches per year. Groundwater is not dramatic. It does not crash or roar, but it is powerful. Without it, more than half the world's drinking water would vanish. Without it, many rivers and lakes would dry out in summer because groundwater feeds them quietly from below. Without it, civilizations, past and present, would never have taken root. Even now, as you lie in bed, there may be a river flowing beneath your feet, invisible, soundless, ancient, carving its path not through valleys, but through grains of sand, particle by particle, drop by drop. And that's the beauty of it. In a world that moves so quickly, groundwater moves slowly. It reminds us that the most essential things in life often happen out of sight, quietly, patiently, always. Beneath your feet, beneath the cities, the forests, and the rolling fields, there is movement. It does not rush. It does not surge. It flows like a sigh, like the slow exhale of the earth herself. This is the movement of groundwater, and though it travels far from the sunlit surface, it is as vital to life as the rain and rivers above. To understand how groundwater flows, we must first return to the aquifer, a word that may sound technical, but in essence simply means a bearer of water. An aquifer is a body of rock or sediment that stores and transmits water through the tiny spaces between particles or fractures in stone. But unlike rivers or streams, where water moves quickly in visible channels, groundwater's path is hidden and much, much slower. A world of pores and spaces. Let us imagine this unseen landscape, not caves or tunnels, as we might picture, but rather a vast maze of microscopic passageways. Imagine sand grains with just enough space between them for water to pass, or rocks like sandstone, where tiny pores, smaller than a hair's width, hold droplets suspended by gravity and time. Some aquifers are made of unconsolidated material, loose sands, gravels, and silts laid down by ancient rivers or glaciers. These are like soft sponges, absorbing water and letting it travel relatively easily. Others are consolidated, made of solid rock like limestone, basalt, or granite. Here, water doesn't move through pores, but through fractures, cracks, and joints, tiny breaks in the rock formed by pressure, heat, or the slow shifting of Earth's crust. Now, the spaces between particles or in the cracks are not all created equal. Two key properties define how water behaves in these underground systems. Porosity, which tells us how much space there is to hold water. Permeability, which tells us how easily water can move through it. You might have a material with high porosity like pumice, a volcanic rock filled with bubbles, but if those bubbles aren't connected, water cannot pass. High porosity, low permeability, a contradiction, a sponge that doesn't leak. In contrast, something like gravel has both high porosity and high permeability. Water moves through it freely. This is the sweet spot for aquifers, a natural balance of storage and flow, the path of least resistance. Water, like many things in nature, follows the path of least resistance. Once it enters the saturated zone, the part of the subsurface where all available spaces are filled with water, it begins to move, pulled gently by hydraulic gradients. These gradients are just differences in elevation or pressure. Like how a ball rolls down a hill, water moves from areas of higher energy to lower energy, but this movement is not fast. In most aquifers, groundwater travels at less than a meter per day. In some tight clays or dense rocks, it may move only a few centimeters per year. Imagine a river that takes a century to travel a mile. This is the defining feature of groundwater: patience. A single drop of rain might take days to reach the water table, and decades, centuries, or even millennia to emerge again at the surface, perhaps bubbling out of a spring or trickling into a stream. Some aquifers hold fossil water so ancient it may have fallen as rain during the last ice age. This water, locked away beneath deserts or mountain basins, has not seen the sky in over 10,000 years. When you hold a glass of groundwater drawn from a deep well, you might be holding liquid time. Darcy's law, the mathematics of movement in the 19th century, a French engineer named Henry Darcy gave us a way to understand how groundwater moves. His equation, elegant in its simplicity, is called Darcy's law, and it describes how water flows through porous materials. In essence, Darcy's law says that the speed of groundwater flow depends on the permeability of the material, how easily it lets water through, the gradient or slope, how steep the change in pressure or elevation is, and the viscosity of the water, which changes with temperature and pressure. This equation is the quiet engine behind much of hydrogeology. It's how scientists predict how fast a contaminant might travel underground, or how long it will take a well to refill, or how far water will spread from a recharge zone. Though mathematical, it tells a very human story, that even the slowest, quietest things can be mapped, understood, and appreciated, confined and unconfined, to faces of an aquifer. Aquifers come in two major types, sun-confined and confined. An unconfined aquifer is open to the surface. Rain can seep directly into it. The water table rises and falls with the seasons, much like a lake does. This kind of aquifer is common in valleys, plains, and coastal areas. It's accessible, but also vulnerable. Pollution from above can easily reach it. A confined aquifer, on the other hand, is sandwiched between two impermeable layers, often clay or solid rock. Water enters this aquifer only where the rock layers are exposed at the surface, often far away from where it is tapped, because it's under pressure. Water in a confined aquifer may rise on its own when a well is drilled into it, sometimes all the way to the surface. These are called artesian wells. In both cases, the water is moving, just slowly and sometimes invisibly. The time it takes for groundwater to travel from its recharge area to where it is used or discharged is called its residence time, and it can range from days to tens of thousands of years. Springs, where the underground comes up, eventually, groundwater re-emerges. Not all of it, not quickly, but steadily. It might seep into rivers and streams, feeding them from below during dry months. It might ooze from a hillside, where the water table intersects with the land surface. Or it might erupt in a bubbling spring crystal, clear and cold, pouring pouring endlessly from the earth. Springs are where the slow flow becomes visible again. They are the earth's quiet exhalations. They have sustained animals, humans, and entire civilizations for millennia. Even when rivers dry, a spring may continue. Even in the harshest desert, one spring can mean life. And yet, all of this flow, this emergence depends on the most delicate balance. The aquifers must stay full. The recharge must match the withdrawal. Otherwise, the slow flow slows further, and eventually stops the human connection today. We rely on groundwater more than ever. About 30% of the world's fresh water comes from underground. In some regions, it's closer to 100%. Entire cities, entire agricultural systems are built on the slow, steady promise of hidden water. But here's the truth: we are pumping it faster than it can flow. Much, much faster. In some places, water that took 10,000 years to collect is being used in a single generation. Aquifers that once flowed freely now sink, causing land to subside. Wells that once bubbled over must now be drilled deeper, and still. Down below, the water moves, quietly, patiently, doing its best to sustain us, even as we test its limits. So the next time you drink a glass of water, or hear the quiet splash of a spring, remember the story it carries: a raindrop's journey, 1,000 slow decisions through rock and time, a rhythm that beats not in seconds, but in centuries. Water beneath our feet, always moving, even when we cannot see it. There are reservoirs beneath us, vast, ancient, and silent, not built by human hands, but carved by time, held by stone, and filled by rain long forgotten. These are the great aquifers of the world, massive underground lakes and rivers that sustain our farms, our cities, and our lives. Though we rarely see them, they are among the most important natural systems on Earth. They are not evenly spread, they are not easily replaced, and yet they flow quietly, steadily beneath deserts, plains, and forests, whispering stories of a deeper world. Let us descend now into these unseen realms and meet the great aquifers that cradle life from below. The Ogallala Aquifer, the drying giant beneath the plains, beneath the heart of the United States. From South Dakota to Texas lies a colossal underground reservoir, the Ogallala Aquifer, stretching over 450,000 square kilometers. It is one of the largest freshwater aquifers in the world. It rests beneath the Great Plains, a region once covered by ancient rivers and windswept sediments. Over time, these sands and gravels settled into thick layers, porous, water-bearing, and ready to store the legacy of countless rains. The Ogallala is not deep by global standards. In some areas, it lies just beneath the surface, but its reach and volume made it a miracle for the American Midwest. In the mid-20th century, farmers discovered that water from the Ogallala could turn arid grasslands into productive farmland. Wells sprang up, irrigation systems spread like veins, crops like wheat, corn, and cotton thrived. For a while, it seemed like the land would bloom forever, but the Ogallala is an ancient aquifer. Much of its water is fossil water, deposited during the last ice age. In most places, it recharges very slowly, if at all, and yet it is being pumped at astonishing rates, far faster than nature can replenish it. In some areas, the water table has dropped by more than 30 meters. Wells go dry, pumps reach deeper, the future becomes uncertain. Still, the aquifer endures, quiet, vast, and holding on. It reminds us that what seems limitless is often fragile, and what lies beneath can be just as vital as what lies above. the Guarani Aquifer, a subterranean sea in South America far to the south. Beneath the lush forests and red earth of Brazil, Argentina, Paraguay, and Uruguay lies another underground giant, the Guarani Aquifer, named after the indigenous Guarani people. This aquifer is one of the largest in the world by volume. It spans over 1.2 million square kilometers, an area larger than France, Germany, and the United Kingdom combined. The Guarani Aquifer holds thousands of cubic kilometers of water, much of it pure and drinkable. It was formed over 200 million years ago, in the early Jurassic, as layers of sandstone were buried by volcanic flows and sealed beneath basalt. Water percolated through cracks in the stone, collecting slowly in vast reservoirs deep beneath the earth. Unlike the Ogallala, the Guarani still receives some recharge from rainfall, especially in the highlands of Brazil, but much of its water too is ancient, having taken thousands of years to collect. It is a source of drinking water for millions. It supports farms, cities, and ecosystems. And yet, much of the aquifer remains untapped and under-researched, depths a mystery, its future uncertain. Concerns are growing about overuse, about contamination, about international cooperation across its 4 guardian nations. But for now, the Guarani sleeps in its stone cradle, cool and clear, flowing slowly through rock and memory. The Nubian sandstone aquifer system, water beneath the desert. Imagine a sea of sand, the Sahara Desert, hot and endless. Dry winds whip across dunes that stretch to the horizon. There is no rain, no rivers, only silence, and yet, deep beneath this barren land, there is water. The Nubian sandstone aquifer system is the largest known fossil water aquifer in the world. It stretches beneath Libya, Egypt, Chad, and Sudan, covering more than 2 million square kilometers. Its water is very old, some over 1 million years. It was deposited when the Sahara was green, lush, and full of lakes and savannas. Now, trapped beneath thick layers of sandstone and shale, this water remains untouched by the modern water cycle in Libya. Massive engineering projects, like the Great Man-Made River, have tapped into this aquifer, piping water across the desert to cities and farms. It is a marvel of human effort, moving fossil water from deep wells to thirsty fields. But there is a cost. The water is not once pumped, it will not return in this way. The Nubian aquifer is both a blessing and a warning, a finite gift from Earth's deep past. Other great aquifers of the world across the globe. Many more aquifers sustain life in quiet ways. The Indo-Gangetic Basin aquifer spans India, Pakistan, Nepal, and Bangladesh. It supports over 400 million people and is vital for agriculture. But overuse and contamination from arsenic and pollutants threaten its health. The North China Plain aquifer provides drinking water and irrigation for millions, yet its levels are falling rapidly due to intensive farming and industry. The Great Artesian Basin in Australia stretches across the arid interior, providing vital water to remote communities and outback ranches. Its artesian springs are culturally sacred to Aboriginal peoples and ecologically unique. Each of these aquifers is a living archive storing not only water, but stories of geology, climate, and human need. Fossil water, liquid timesome of the water we draw from these aquifers, is what scientists call fossil water. This is not water from fossils, it is water as fossiler, relic of past climates, sealed underground long ago. In many arid regions, it represents the only accessible water source, even though it was last replenished thousands to tens of thousands of years ago. fossil water is finite. Once it is gone, it may not return for thousands of years, if ever. Yet it is often treated like an endless supply, pumped rapidly, irrigated lavishly, used as though time has no cost. Some aquifers, like parts of the Ogallala Nubian or Arabian systems, are being mined, not tapped. That is, we are using more than is naturally added back. We are drawing down the past to serve the present. The concept is haunting. We drink the rain of mammoths. We irrigate with ice age floods. We turn deep time into daily life, sustaining agriculture, sustaining life globally. Over 70% of all groundwater use goes to agriculture. Crops that feed billions depend on invisible rivers underground. Without groundwater, much of the world's food supply would vanish. Arid regions would dry. Cities would struggle. Life would thin. But groundwater is not invincible. When we aquifers collapse. When we pollute, they can take centuries to recover. When we forget their limits, we risk everything that flows from them. Sustainable groundwater use means thinking in longer timelines, planting crops that match the climate, using drip irrigation, recharging aquifers with rainwater, protecting recharge zones from paving and pollution. It means honoring the patience of water, an ancient gift, a modern responsibility. The aquifers of the world are not merely water sources. They are geological miracles, climate archives, and pillars of civilization. They have outlived empires. They have carried rivers beneath deserts. They have whispered upward through springs and wells, through hands and histories. And now they call on us to listen, to slow down, to match their pace, if only a little. For in the slowness of groundwater lies a kind of wisdom, the understanding that what matters most is often hidden, patient, and quietly sustaining. Let us honor it beneath our feet. Water sleeps, but it is not asleep without dreams. It shifts, it breathes, it flows in hidden ways. Groundwater is not static. It is part of a living cycle, a rhythm that spans sky and stone, cloud and soil. Each drop we pump from deep below was once a whisper in the rain, a ripple in a stream, a glint on the surface of a quiet lake. And just as water can descend into the earth, it must also return. This returning is recharge. The earth gives us water from beneath, but she also needs time to refill, a fragile balance between what we take and what she can offer back. Let us now trace the quiet journey of groundwater's renewal and the subtle ways it can be disrupted. The rain's descent, recharge from precipitation. All recharge begins with rainfall. As drops fall from clouds and kiss the land, they seek many paths. Some gather on leaves and evaporate. Some run swiftly downhill, joining rivers and seas. But some, the quiet ones, sink in, through blades of grass, through sandy fields, through porous earth. Rain seeps downward, slowly, steadily, patiently. If the soil is permeable, if the surface is not hardened by concrete or clay, this water continues its descent, passing through layers of dirt and stone. It filters and slows, cleansed by the earth itself. Eventually, it may reach the saturated zone, the deep spaces between rocks that are completely filled with water. There, it becomes part of the aquifer, a recharge complete. This process can take days or decades. In some places, it is quick. In others, agonizingly slow. But every drop that reaches the aquifer is a tiny act of renewal. In regions where rain is steady and the ground is kind, this natural recharge can keep pace with human use. But in arid zones, or places where the surface is sealed by roads and rooftops. Rainfall runs away before it can seep in. The sky offers gifts, but only the patient earth can accept them. The gift of rivers and lakes, surface water, is not the only source of recharge. Rivers, lakes, and wetlands also give to the ground in some regions. Rivers lose water to the earth beneath them, called losing streams. They are like leaky veins, their waters seeping downward through gravel beds and sandy banks. This kind of recharge can be rapid, especially after floods or heavy rains. The swollen river spills over its banks, and the water filters into the floodplain, nourishing not just plants, but aquifers deep below. Lakes, too, can act as recharge zones, especially if their beds are permeable. Water can slowly drain downward, a hidden connection between still surfaces and subterranean stores. Wetlands are especially rich in recharge potential. Their saturated soils and seasonal floods make them natural filters and sponges, holding water and allowing it to percolate at a gentle pace. These surface waters are bridges, places where the visible and invisible water worlds touch. But like all bridges, they are vulnerable. Dams, diversions, and pollution can cut the flow. When rivers no longer reach the land they once fed, recharge fades. The earth does not demand much, but she asks for flow. She asks for time, forests, fields, and urban footprints. What helps, what hurts not. All landscapes recharge equally. Forests, with their deep-rooted trees and sponge-like soils, are excellent recharge zones. Leaves slow, the rain roots open the earth. Organic matter holds moisture like a gentle hand. Grasslands and farmlands, when cared for, also help recharge, especially if plowed gently, mulched, or covered with vegetation year-round. They allow rain to seep instead of run. But when the land is stripped bare by overgrazing, deforestation, or erosion, rain runs faster. It cuts the surface, carries soil, and escapes before it can soak in. And then there are cities. Urban areas, paved with asphalt and concrete, are almost entirely closed to recharge. Rain hits the surface and rushes into drains. Rooftops collect water, but rarely return it to the ground. Sidewalks and streets turn every storm into a flood. Not a gift. The more we pave, the less the earth can drink. Some cities have begun to undo this, adding permeable pavements, rain gardens, and green roofs. These let water slow down, find its way back into the ground. It is a small but vital act of kindness, letting the earth breathe beneath our buildings. Depletion, when the balance breaks, groundwater can take centuries to fill, but it can be emptied in years. Depletion happens when we withdraw more water than nature can replace. It is the silent crisis of our time. Wells are drilled deeper, pumps grow stronger, the water table drops inch by inch, foot by foot. In some places, the land itself begins to sink, a process called subsidences. Empty aquifers collapse under the weight of rock and time. Once the pressure is lost, the aquifer cannot hold as much. It cannot refill. The space is crushed. The loss is permanent. Irrigated agriculture, especially in dry regions, is the largest driver of depletion. Crops like rice, sugarcane, and cotton demand more water than the land can spare. Vast green fields bloom in the desert, but beneath them, the aquifers bleed. Cities, too, grow thirsty. Industry expands, populations rise, and the hidden waters fall. In many regions, California's Central Valley, India's Punjab, parts of northern China, the rate of withdrawal far exceeds recharge. The balance tilts. The system strains. The earth is patient, but she is not infinite, artificial. Recharge, giving back, mindfully, but all is not lost. Humans have also found ways to help recharge groundwater. Through artificial recharge, we return water to the earth on purpose. Recharge wells inject stormwater or treated wastewater deep into aquifers. Recharge basins, shallow ponds, or trenches liao rain to pool and slowly seep into the ground. Urban stormwater capture collects rain from rooftops and streets, filters it, and sends it below. Even simple practices like planting trees, building terraces, or allowing fields to rest between harvests can make a difference. These are not quick fixes, but they are acts of balance. They say, we remember, we care, we return what we can. The rhythm of enough groundwater is the earth's quiet savings account. We draw from it in times of need, drought, heat, growth. But like any savings, it depends on what we put back. Recharge is slow. It needs patience, space, stillness. It does not shout. But it matters more than we know. Each raindrop that seeps, each stream that lingers, each tree that drinks and holds, they are part of a rhythm, a promise that the water beneath us will not fade if we let it rest, if we let it breathe. Let us hold that balance close, not in fear, but in care. For the world beneath is not infinite, but it is enough if we listen and give it time. Beneath the soil, groundwater flows silently, clean, cool, and hidden. For centuries, it has been a wellspring of life, untouched by surface noise. But the world above is no longer gentle. Today, there are silent invaders in the underground, pollutants. They arrive slowly, invisibly. They seep, trickle, dissolve, and once they reach the water table, they linger for years, decades, or longer. Groundwater moves slowly. This makes it a faithful storage of purity, but also a victim of persistence. When contaminated, groundwater cannot easily flush itself clean. It becomes a trap holding within it the memory of our mistakes. This chapter is a journey into the hidden dangers below the surface, the many ways that pollution reaches the aquifers, and the quiet crisis it leaves behind, the long road down. How pollution travels. Pollution does not fall all at once. It begins with a drip, a leak, a careless spill. It seeps through layers of soil, sometimes quickly through sandy or fractured rock, sometimes slowly through compact clay and silt. But eventually, gravity pulls it downward, drop by drop, toward the saturated zone where groundwater resides. There, it mingles with the water that we drink, pump, and rely on. Unlike rivers, aquifers do not carry pollution away. There is no escape downstream. There is only absorption. Agricultural runoff, a hidden cost of food. One of the largest sources of groundwater pollution is agriculture. To grow more crops, farmers use fertilizers rich in nitrogen and phosphorus. These chemicals help plants flourish, but what the crops do not use, the soil cannot always hold. When it rains, nitrates seep through the earth and into the groundwater. This is especially dangerous in regions with sandy soils and shallow aquifers. Nitrates in drinking water can cause serious health issues, especially for infants, leading to conditions like blue baby syndrome. The contamination is colorless, tasteless, and odorless, easy to miss until it is too late. Pesticides and herbicides follow a similar path. Sprayed to protect crops, they are often soluble and persistent. They dissolve in water, travel with it, and remain stable underground. These chemicals were designed to kill, and even in trace amounts, they can disrupt ecosystems, damage wildlife, and harm human health over time. We feed ourselves from the land, but sometimes the price is water poisoned in silence. Industrial pollution, heavy metals, toxic waste, and forgotten drums do not just make things, they also leave behind waste in the past. Much of this waste was dumped, buried, or abandoned, often without safeguards. Toxic chemicals, lead, arsenic, mercury, chromium, benzene, and many more now lie beneath old industrial sites. Leaking slowly into the soil, these hazardous substances are heavy, persistent, potent. Once underground, they do not disappear. Some bind to soil particles, others dissolve into groundwater, where they move through aquifers and wells. The contamination may travel miles from its original source. In some cases, underground storage tanks, especially older steel ones, have corroded and leaked fuel or chemicals directly into the water table. Even today, thousands of such tanks remain in use out of sight, but still a threat. And then there are the legacy sites, abandoned mines, forgotten waste pits, and closed factories whose secrets continue to seep. The pollution is slow, the damage is deep, the cleanup is expensive, and often the source is long gone before the harm is ever discovered. Urban waste, sewage, septic systems, and landfill cities do not always keep their water and waste separate. In many rural and suburban areas, homes rely on septic tanks. These underground systems are designed to treat household wastewater, but when poorly maintained, overloaded, or built in unsuitable soils, they can leak, allowing bacteria, viruses, and nutrients to reach the groundwater. Sewage leaks, often unnoticed, can do the same, especially when infrastructure ages and pipes crack under pressure. Landfills, too, are a concern. Though modern sites are lined and monitored, older landfills were often little more than holes in the ground. Rainwater percolates through the trash, forming leachate, a toxic brew of chemicals, metals, and microbes that can enter the groundwater below. Even stormwater runoff, picking up oil, grease, metals, and debris from streets and sidewalks, can soak into the ground when unfiltered. Our daily waste is not gone when we throw it away. Much of it continues its journey below the surface. Salinization, the salt that rises. Not all pollutants are industrial or chemical. Sometimes it is the salt we must fear. Salinization occurs when groundwater becomes salty, often due to excessive irrigation in dry areas. As water evaporates from the surface or is drawn up by plants, it leaves behind dissolved salts. Over time, if the aquifer is not flushed or replenished with fresh water, the concentration of salt increases in coastal regions. The threat comes from saltwater intrusion. When we pump too much fresh water from a coastal aquifer, the natural balance is disturbed. Seawater creeps in to take its place, contaminating wells and farmland with briny water that cannot be used for drinking or irrigation. Salt may be invisible at first, but it makes the land sterile. It ruins taste. It corrodes pipes, and once it enters an aquifer, it is nearly impossible to remove. Contamination from fracking and drilling, modern energy extraction, also threatens groundwater. In hydraulic fracking, high-pressure fluids are injected underground to fracture rock and release oil or gas. But the chemicals used in this process, many of them toxic, can migrate into nearby aquifers through faults, fractures, or poorly sealed wells. Oil and gas drilling sites can also leak hydrocarbons into the groundwater, especially if well casings fail or spills occur at the surface. These forms of contamination are controversial and often underreported, but the risk is real, especially in areas where aquifers lie close to the rock layers being drilled. The thirst for energy, like the thirst for water, runs deep, but when the two collide, the consequences ripple silently underground. The challenge of cleanup, unlike surface water, groundwater cannot be easily skimmed, flushed, or filtered once polluted. Contamination may remain for decades, traveling slowly through the aquifer like a shadow that refuses to lift. Pump and treat systems, where water is pumped to the surface and cleaned, are expensive and often slow in situ treatments, such as injecting microbes or chemicals to break down pollutants underground, are still developing and not always effective. In many places, once groundwater is polluted, the damage is irreversible. Prevention is far easier than cure. A call to care groundwater gives life silently, but pollution reaches it just as quietly. No alarms, no warning signs, just a slow, invisible unraveling till a well runs foul, a child falls ill, or a farmer finds salt in the soil. If we are to protect the waters below, we must think above. About every drop we spray, every tank we bury, every chemical we throw away. The earth remembers, and the water holds what we give it for. Better or for worse, let us walk gently, let us act wisely, for beneath our feet lies a treasure we cannot afford to lose. Beneath the fields, forests, and cities lies a world unseen, a realm of silence, a realm without sunlight, a world that breathes in the darkness. This is the subterranean ecosystem, the secret life below, and though hidden, it is far from lifeless. Inside deep aquifers and shadowy cave systems, life has adapted in astonishing ways. Blind, colorless, and slow, these organisms exist in the quiet flow of groundwater, surviving without light, enduring without sound, and thriving in isolation. This chapter is a journey into that deep, dark worlder place where evolution has taken strange turns, where biology whispers instead of shouts, and where the presence of life reminds us that water, even underground, is never truly alone. Stygobians, creatures of the groundwater life. In groundwater is not easy. There is no sunlight to provide energy through photosynthesis. Food is scarce. Space is tight. The water moves slowly. Oxygen is limited, and the temperatures are constant and cool. Yet, in these extreme conditions, nature has carved out a unique community. Stygobians, organisms that live entirely and exclusively in groundwater systems. They are often blind because light never reaches them. Eyes are unnecessary, colorless, or translucent without sunlight. Pigmentation offers no benefit. Small and elongated to move easily through narrow underground pores. Slow-growing and long-lived because energy is scarce. Every movement must be efficient. These adaptations are not signs of weakness, but of specialization. Stygobians have evolved to thrive in a world where change is slow and survival depends on precision. Types of groundwater life. 1. Crustaceans. Tiny amphipods, isopods, and copepods are among the most common groundwater animals. These shrimp-like creatures live in gravel-filled aquifers, feeding on organic matter that seeps down from above. Some species are found nowhere else on Earth, locked in isolated pockets of rock. Their ancestors having lived underground for millions of years. 2. Flatworms and worms. Some groundwater ecosystems are home to planarians and oligo-shaped worms. These tiny scavengers glide through water-saturated spaces, breaking down detritus and recycling nutrients. 3. Snails and molluskin. Certain caste systems, small aquatic snails and other mollusks, can be found clinging to submerged surfaces, scraping away biofilm or algae. For microbial life, though invisible to the naked eye, microbes dominate the underground. Bacteria and archaea feed on minerals, break down organic matter, and form the base of the subterranean food web. Some even consume iron, sulfur, or methane, creating energy without sunlight. These microbes can survive in total darkness, and some live miles underground. In rocks once thought to be sterile, they are ancient, they are everywhere, and they may hold clues to life on other planets. Cave systems, islands of darkness where aquifers flow through limestone. They often form karst systems, networks of caves, sinkholes, and underground rivers. These caves are not only geological marvels, but biological ones too. They support rich troglodytic life organisms that live entirely in caves and never see daylight. Some notable cave species include blind cavefish, found in Mexico and other regions. These fish have lost their eyes and pigment over generations. Cave salamanders, amphibians that live in damp, dark chambers. Cave beetles and spiders, tiny predators adapted to hunt in pitch blackness. Unlike stygobionts, which live in water-filled pores and aquifers, troglobites roam through open cave chambers, but their adaptations are similar. Blindness, pale skin, heightened senses of smell and vibration. These species are often incredibly rare, and many are endemic, found only in a single cave system or region, that makes them especially vulnerable to disturbance or pollution. Ecological roles more than survivors. These underground creatures may be small, but they play critical roles in the health of the aquifer environment. Microbes help purify water, breaking down pollutants and organic matter. Crustaceans and worms help cycle nutrients, keeping ecosystems balanced. Predators help control populations and prevent overgrowth. In essence, they create a quiet but vital ecological web beneath our feet. When these organisms begin to vanish, it is often a sign that the groundwater itself is under threat, contaminated, depleted, or disrupted. They are, in a way, our early warning system. Extreme survivors. Life in the deep biosphere. Recent research has revealed that life does not stop at the water table. Beneath the crust of the earth, as deep as 5 kilometers, microbes have been found living in the pores of rock, surviving on hydrogen, methane, and minerals. This deep biosphere may represent one of the largest reservoirs of life on Earth by mass, yet it remains almost entirely unexplored. These organisms live without sunlight, without oxygen, and in crushing pressure. Their lifespans are measured not in years, but millennia. Some may divide only once every 1,000 years. This hidden biosphere reminds us, wherever there is water, no matter how deep or dark, life finds a way. Threats to subterranean life, though protected by rock and time. Groundwater life is not immune to danger. Pollution from chemicals, sewage, or oil can poison aquifers and kill sensitive species. Overpumping lowers water tables, drying out habitats. Construction and mining can collapse cave systems or block underground flows. Climate change alters recharge patterns and water chemistry. Many subterranean species are unknown to science. They vanish before they are even discovered. To protect them, we must treat groundwater not just as a resource, but as a habitat, a world worth knowing. We often imagine wilderness as forests, oceans, and deserts, But the deepest wilderness is below. It is cold and dark. It whispers instead of roars. It is inhabited by things without eyes, without names, without fame. Yet it is filled with life, fragile, patient, ancient, and it deserves our attention. The next time you drink from a well or feel the coolness of spring water, remember, you are touching a world where life waits in silence, a world that has endured for eons and asks only to be left in peace beneath our feet. Far below the plow lines and pipelines lies water that is older than civilization, older than cities, writing, or even human memory. Some of it fell as rain, thousands, even millions of years ago, when woolly mammoths still roamed the steppes and vast ice sheets covered continents. These ancient waters, sealed within deep aquifers, are not just reservoirs of life, they are time capsules. Groundwater, in its quiet and hidden way, tells stories. It carries signatures of the past, of climates long gone, ecosystems long faded, and atmospheric conditions that shaped the course of Earth's history. Scientists have learned to read these stories, to pull from the depths of the planet a kind of diary written in water. In this chapter, we explore how groundwater reveals the shifting moods of Earth's climate across millennia. From deserts that were once green to frozen landscapes that once flowed with rivers, the evidence lies in the chemistry, age, and movement of water buried deep underground. Fossil water, the memory of rain. Not all groundwater is part of the modern water cycle. Some aquifers contain what is called fossil water, ancient groundwater that has not been replenished since prehistoric times. It is often trapped deep underground, isolated from the surface by impermeable rock layers, because it does not mix with today's rainwater. It retains the chemical fingerprints of the world when it first fell. Take, for instance, the Nubian sandstone aquifer system beneath the Sahara Desert. Some of its water is more than 30,000 years old, dating back to a time when the Sahara was a savanna filled with lakes, trees, and wildlife. Back then, the climate was wetter and rains were regular. Over time, as global climate patterns shifted and the region became arid, the rainfall disappeared, but the water remained underground, untouched. By analyzing this fossil water, scientists can reconstruct what the atmosphere and climate were like during that wetter time. The temperature, precipitation patterns, and even the vegetation of the past are all encoded in the isotopes and dissolved gases within this ancient water. Isotopes, nature's clocks and thermometers. To understand the past, scientists often turn to isotopes, atoms of the same element with different numbers of neutrons. Two of the most important in groundwater research are oxygen 18O and deuterium-H. These stable isotopes of oxygen and hydrogen can tell us about the temperature and origin of the water at the time it was formed. Carbon-14C and chlorine-36Cl. These radioactive isotopes allow scientists to date groundwater, often going back tens of thousands of years. For example, colder climates produce lighter isotopes in precipitation. So, if a sample of groundwater has a low ratio of heavy isotopes, it likely fell during a glacial period. By mapping the isotope ratios in aquifers around the world, researchers can piece together a climate mosaic: when it rained, how much, and under what temperatures. In this way, groundwater becomes a geological thermometer, silently preserving the record of ancient skies. Paleoclimate archives in water, much like ice cores from Antarctica or tree rings in old forests. Aquifers serve as archives of paleoclimates, the study of past climate conditions. In places like Australia, North Africa, and the Middle East, ancient Groundwater has been found with isotopic compositions that clearly indicate wetter climates in the distant past. These findings match with archaeological records, showing that humans once thrived in areas that are now uninhabitable deserts in South America. The Guarani Aquifer contains water that fell during the last ice age. By comparing that water with modern rainfall, scientists can track how the Amazon basin's climate has changed over 20,000 years in Greenland and Antarctica. Subglacial lakes and groundwater systems beneath thick ice sheets offer another kind of climate record, trapped for millions of years. These waters tell of Earth's coldest epochs and the subtle shifts that began to thaw the ice. Each aquifer is like a buried book, its pages written in isotopes, gases and ions, noble gases and ancient atmospheres. Addition to isotopes, groundwater contains dissolved gases that provide insight into ancient environments. Among the most telling are the noble gases helium, neon, argon, krypton, and xenon. These gases do not react chemically, so their concentrations in water reflect the temperature and pressure of the air when the water infiltrated the ground. By measuring noble gas concentrations in ancient groundwater, scientists can estimate the air temperature when the water entered the aquifer, the atmospheric pressure and composition at that time, possible volcanic or solar events that affected the air. For instance, a spike in certain noble gas levels might suggest a nearby volcanic eruption, while a consistent temperature profile over centuries can confirm long periods of climatic stability or change. These gas signatures are subtle, but their meaning is profound. They offer a glimpse into the invisible air of Earth's deep past. What ancient groundwater tells us about the future. Understanding how climate has shifted in the past helps us prepare for the future. Ancient groundwater records can reveal how quickly climates have changed before, and what ecosystems survived or collapsed, how rainfall patterns moved across continents where ancient droughts occurred, and how long they lasted. This information helps scientists model potential impacts of current climate change. For instance, if an aquifer shows that the region has been dry for the last 10,000 years, and we are now withdrawing large volumes of that fossil water, it's clear we are using a resource that is not renewable on human timescales. Furthermore, ancient groundwater helps validate climate models, ensuring their accuracy. If a model predicts a glacial climate 20,000 years ago, and isotope data from aquifers confirm it, confidence in the model grows. The ethical legacy of ancient water's fossil water is a finite resource. Much like oil, once used, it does not return in any meaningful time frame. In regions like the Middle East, North Africa, and parts of Central Asia, countries rely heavily on fossil aquifers for irrigation and drinking water. But as the water table drops and wells run dry, questions arise. Are we drawing too heavily from a non-renewable past? Should ancient water be preserved for future generations? What right do we have to drain an archive of Earth's memory for short-term gain? These are not merely scientific questions, they are ethical ones. The past is whispering through the deep. Are we listening? Conclusion: messages from below groundwater is more than just water. It is memory. It is history in motion. Each drop holds a fragment of Earth's ancient weather. Each aquifer is a silent witness to the planet's transformations. And every time we study these hidden reservoirs, we read a little more of the story that connects us to ice ages, rainforests, deserts, and oceans long gone. The ground beneath us does not forget. If we learn to listen, it can teach us where we have been and where we might go next. As humanity steps into an uncertain future marked by climate change, growing populations, and vanishing surface water, we are turning more than ever to the hidden rivers beneath our feet. Groundwater, so often taken for granted, is becoming one of our most precious lifelines. But even as we draw deeper and faster from the earth, the question echoes louder. Can we use this invisible resource without destroying it? This chapter explores the road ahead. How can we use groundwater sustainably, ensuring it remains a source of life for generations to come? What new tools and technologies are emerging to help us better understand, manage, and protect this ancient water? And perhaps, most importantly, how do we balance human need with planetary health? The rising demand, the need for groundwater, has never been greater. Agriculture, industry, and drinking water demand are pushing aquifers to their limits. In many places, from India's Punjab to California's Central Valley, wells are being drilled deeper every year, chasing falling water tables. Yet the problem is not just overuse, it is also misuse. Leaky pipes, inefficient irrigation, unregulated pumping, and poor monitoring mean that vast quantities of groundwater are wasted or mismanaged. The result? Aquifers collapse, land sinks, and ecosystems vanish. If we are to survive the 21st century without depleting the very ground beneath us, a shift is needed from extraction to stewardship. Sustainable use, the path to balanced sustainability in groundwater, means using water at a rate that does not exceed its natural recharge. In other words, we should not take more than what nature can replenish. Achieving this requires careful planning, community cooperation, and policy enforcement. Here are some key strategies. 1. Regulated pumping. In many countries, groundwater pumping remains unregulated. Anyone can drill a well and extract water with little oversight. Enforcing limits through permits, quotas, or tiered pricing can reduce over-extraction and promote conservation. 2. Managed aquifer recharge. Instead of relying solely on nature to recharge aquifers, some regions are now helping the process along. MAR involves capturing rainwater, floodwater, or treated wastewater and allowing it to seep back into the ground through special recharge basins, injection wells, or riverbeds. This technique is already being used successfully in Australia, Spain, and parts of the United States. 3. Efficient irrigation. Agriculture consumes around 70% of the world's groundwater. Switching from flood irrigation to drip or sprinkler systems can reduce water use by 30 to 50%. In places like Israel, such technologies have transformed dry landscapes into productive farmland while preserving groundwater for crop choices and water budgets. Some crops are water-thirsty by nature. Growing them in dry regions puts undue stress on aquifers. Adopting water-wise cropping systems such as drought-resistant varieties or native plants can make farming more sustainable. Additionally, setting local water budgets ensures that communities use only as much as their aquifers can safely provide. The role of technology is rapidly transforming our relationship with groundwater. From satellites to smart pumps, we now have tools that can see, track, and even predict what once was hidden. 1. Remote sensing and satellites. Essays GRACE, Gravity, Recovery, and Climate Experiment. Satellites can measure changes in Earth's gravity caused by shifting water masses. This allows scientists to monitor groundwater depletion from space without drilling a single hole. These satellite observations have revealed alarming trends, such as severe aquifer decline in northern India and parts of China. 2. Smart wells and sensors. Modern wells can be equipped with sensors that provide real-time data on water levels, salinity, temperature, and flow rates. This helps farmers and managers make informed decisions, like when to irrigate or when to cut back. Point 3. Artificial intelligence and big data AI and machine learning are being used to analyze massive datasets on rainfall, soil, moisture, pumping rates, and aquifer health. These tools can forecast droughts, optimize irrigation schedules, and identify risks of overuse long before they become crises. 4. Groundwater. Mapping and modeling. Advanced computer models allow researchers to create detailed 3D maps of aquifers showing where the water is, how it moves, and what risks exist. With these models, planners can simulate different scenarios. What happens if rainfall drops 10%? How will an increase in farming affect recharge rates? Such simulations guide smarter policies. Desalination and groundwater banking in coastal areas. Overpumping can cause salty seawater to invade freshwater aquifers, a process known as saltwater intrusion. One solution is desalination, which removes salt from seawater to produce fresh drinking water. Though expensive and energy-intensive, new innovations are making it more viable, especially in places like Saudi Arabia and Israel. Another promising idea is groundwater banking. In wet years, surplus water is stored underground instead of being lost to runoff. Then, in dry years, that water can be pumped out for use. This strategy acts like a savings account, helping regions ride out droughts without overexploiting natural recharge. Community-led solutions. Sustainable groundwater management is not just about high-tech tools. It also requires human trust, cooperation, and local leadership. Some of the most successful examples of groundwater stewardship come from grassroots efforts. In Andhra Pradesh, India, farmers have formed water user associations that monitor wells, share data, and plan irrigation together. In California, groundwater sustainability agencies now include farmers, urban planners, and conservationists, all working under one roof to manage shared aquifers. Education also plays a key role. When people understand where their water comes from and what threatens it, they are more likely to use it wisely. The ethical frontier as technology improves and water stress grows. Questions of fairness and ethics rise to the surface. Who owns the water under the ground? Should private companies be allowed to bottle and sell fossil water? What happens when one region's pumping dries up wells in another? These are not simple questions, but they force us to think long-term, to see groundwater not as a commodity, but as a shared legacy. Conclusion: a future written in water. Groundwater is not just a hidden source of life. It is a test of foresight, of restraint, and of imagination. As we face the future, we must ask ourselves, can we learn to live with the patience of rain and the humility of the aquifer? With smart policies, new technologies, and a deeper respect for the unseen, we can build a future where groundwater flows, not just for us but for those who will walk this earth long after we are gone. The tools are here, the knowledge is growing. What remains is the will to listen to the quiet pulse beneath our feet, hidden beneath the ground. Away from the eyes of most, groundwater quietly supports half the world's population. It waters fields, quenches thirst, powers industries, and sustains entire ecosystems. But now, that silence is beginning to break. From deserts in the Middle East to rice fields in Asia, wells are running dry. What was once considered infinite is proving alarmingly finite. The global groundwater crisis is not a distant threat, it is already here. This chapter dives into the growing crisis, where and why groundwater is being overused, what happens when it disappears, and how competition for water can turn into conflict. It is a story not only of resource exhaustion, but of political tension, human struggle, and an urgent need for action. Overpumping, the hidden drain in many parts of the world. Groundwater is being pumped far faster than it can be replenished, known as groundwater overdraft. This process slowly empties aquifers that took thousands, even millions of years to fill. The consequences of overpumping are not just environmental, they are also economic, social, and political. In India, millions of farmers depend on groundwater for irrigation, but with no limits on extraction. Wells are now being drilled deeper and deeper, often hitting salty or toxic water. Some villages that once thrived now lie abandoned. In California, years of pumping for agriculture have caused land to sink. This process, called subsidence, has damaged roads, canals, and infrastructure. In Saudi Arabia, vast underground reserves of fossil water once made the desert bloom, but after years of wheat farming, many of those reserves are gone likely forever. These examples are just the surface of a global pattern. Short-term gains followed by long-term loss. Aquifers under stress. The hotspots of the world's most critical aquifers are now under severe stress. Satellite data from NASA's GRACE mission has revealed where groundwater depletion is most alarming. The North China Plain Aquifer, home to over 100 million people and one of the country's main agricultural zones. This aquifer has dropped dramatically over the past 2 decades. The Indus Basin, Pakistan and northwest India, shared by 2 nations. This aquifer supports millions of farmers and is being rapidly depleted due to excessive irrigation. The Central Valley Aquifer, California, USA, a backbone of US agriculture. It's losing water at one of the fastest rates on Earth. The Arabian Aquifer system, underneath countries like Saudi Arabia and Kuwait. This fossil aquifer is being heavily drained for urban use and food security. These aquifers are not just underground lakes. They are the hidden foundations of regional stability. When they fail, the impacts ripple outward. What happens when water runs out? Groundwater does not disappear overnight, but as water tables fall, the cost of pumping rises. Poorer communities are often the first to suffer. Wells dry up, crops fail, and families are forced to migrate. In Iran, thousands of villages have become uninhabitable due to water scarcity. In Yemen, ongoing conflict has been partly fueled by struggles over dwindling water supplies. In Mexico, groundwater depletion has caused entire towns to sink, cracking roads and splitting homes apart. Sometimes, the problem is invisible till it is too late. Saltwater intrusion, caused by overpumping in coastal areas, can turn one's fresh aquifers permanently brackish. In parts of Bangladesh, this has contaminated wells and driven communities to rely on polluted surface sources. When scarcity breeds conflict, water scarcity alone does not cause war. But when it intersects with poverty, inequality, weak governance, or political instability, it can become explosive. Tensions between farmers and cities in many regions. Agriculture uses the lion's share of groundwater, sometimes up to 90%, but as cities grow, they often tap the same aquifers. This can lead to tension between rural and urban users. In India, violent protests have erupted when water was redirected from farms to cities, like Chennai or Bengaluru. Cross-border aquifers. Many aquifers span national boundaries, but unlike rivers, which are governed by international treaties, transboundary aquifers often lack clear legal frameworks. The Nubian sandstone aquifer system, shared by Libya, Chad, Sudan, and Egypt, is a prime example. If one country overuses it, others may suffer. But there is no global authority to intervene. Privatization and inequality in some places. Large corporations have gained control of groundwater for bottling or industrial use. In South America, foreign companies have purchased rights to deep aquifers while local communities struggle for access. This raises ethical questions. Should groundwater be a public good or a private commodity? Signs of a turning tide. Despite the growing crisis, there are glimmers of hope. Awareness is spreading, and more countries are recognizing the urgency of groundwater management. In California, the Sustainable Groundwater Management Act, SGMA, now requires local agencies to balance groundwater use and recharge. In Jordan, one of the world's driest countries, advanced metering and regulation have reduced illegal pumping. In South Africa, laws require permits for groundwater extraction, and community-led programs are helping manage local aquifers. Sustainably. There is also increasing scientific cooperation. The UNESCO International Groundwater Resources Assessment Center (IGRAC) is working to map and monitor the world's aquifers, while new data from satellites, sensors, and AI help predict risks before they become disasters. What needs to change? Solving the groundwater crisis is not about a single fix. It requires a shift in how we value, use, and protect water, data, and transparency. Many countries still lack basic data on groundwater levels, quality, and usage. Investments in monitoring are essential. Fair regulation. Groundwater laws must be enforced and designed to protect both people and the environment. This includes capping usage, controlling well drilling, and penalizing waste. Equity and access. Water must be accessible to all, not just those who can afford to drill deeper. Conflict prevention. Diplomacy around shared aquifers should be proactive, not reactive. Trust building, data sharing, and joint planning can prevent disputes. But perhaps the most important change is cultural. Groundwater must no longer be treated as an endless reserve. It is a gift from the past, alone from the earth that we are borrowing from the future. Conclusion: digging deeper than water. The groundwater crisis is not just a technical problem, it is a human one. It challenges how we share, govern, and care for a resource that sustains life but remains out of sight. If we ignore it, the consequences will be widespread and irreversible. But if we act wisely, with foresight and fairness, we can turn crisis into opportunity. The aquifers still flow. There is still time to change course. But we must listen to the silence beneath our feet and respond before it becomes permanent. Beneath the surface of the earth, in the deep silence, below our homes, farms, cities, and forests, water moves slowly, gently, eternally. It carves its quiet path through sand, gravel, and stone, unseen but constant. Groundwater does not roar like rivers or crash like waves. It hums, it pulses, it breathes with the planet itself. This final chapter is not a call to action or a list of solutions. It is a reflection, a chance to pause and consider the timeless, hidden presence that has shaped life since the beginning. Water in the dark, a memory of rain. Each drop of groundwater began its journey long ago. It may have fallen as rain centuries or millennia in the past. It may have filtered slowly through leaves, roots, and soil before slipping into the earth's embrace. Some of it may have come from a time when woolly mammoths roamed the plains, or when deserts were green. Groundwater is more than a resource. It is memory, liquid history. It holds within it the story of climates long gone, of ancient forests, of shifting continents and forgotten rain. To draw water from a deep aquifer is to touch something ancient, something patient. It humbles us. It reminds us how briefly we walk the earth. The pulse of life, though we cannot see it, groundwater sustains more than crops and cities. It feeds wetlands, forests, and rivers. It gives breath to desert oases and nourishes life in the darkest caves. Tiny blind fish, shrimp, and microorganisms live entire lives in the silent dark, evolving slowly over millennia. Untouched by light to these creatures, groundwater is not hidden, it is home. And for humans too, it has always been more than practical. Long before modern plumbing, people found springs sacred. Pilgrims journeyed to holy wells. Cultures honored the spirits of underground water. In myths, caves and aquifers were doorways to the underworld, sources of rebirth, places of mystery. Even today, a cold sip from a deep well can feel like more than refreshment. It feels like a blessing. Slowness, stillness, strength in a world driven by speed. Groundwater moves slowly. It teaches us another rhythm, the rhythm of the earth. Some aquifers refill over decades, others over thousands of years. They ask for patience, restraint, and care. There is a lesson in that slowness. Not all solutions lie in urgency. Some are found in quiet stewardship, in letting the land rest, in listening before acting. Groundwater invites us to think in longer time frames, in generations, not just seasons. The earth is old, its water is older, and the balance it offers is not flashy or loud, but deep and enduring. A mirror for ourselves. Our relationship with groundwater is, in many ways, a reflection of our relationship with the planet itself. Do we take without giving? Do we value what we cannot see? Do we plan only for today, or do we care for tomorrow? To care for groundwater is to care for what lies beneath the unseen, the ignored, the buried truths. It asks us to look deeper, not just into the earth, but into ourselves, and perhaps, in that reflection, we find something powerful. Humility, the gentle future. The road ahead is not easy. There will be challenges, dry wells, competing needs, climate shifts. But the story of groundwater is not only one of crisis, it is also one of resilience. Aquifers can recover, springs can return. What is broken can often be healed if we choose wisely. Technology will help, policy will matter, but so will wisdom, so will kindness, so will the simple act of leaving enough behind for others, other people, other creatures, other times. The future can still hold water. It can still hold grace. Final thoughts? The flow below there is something comforting in knowing that even as we sleep, water moves slowly below us. It does not seek attention. It asks only to be respected. In its silence, it speaks. In its patience, it teaches. In its hiddenness, it offers a mystery we may never fully understand. Perhaps we are not meant to. Perhaps part of the beauty of groundwater is that it reminds us not everything must be seen to be valued. Not everything loud is lasting. As we step forward into a warming world, let us remember the calm beneath. Let us draw not just from the well, but from the wisdom it represents, and let us walk with gentler feet over the veins of the earth, knowing that below, in the deep, the eternal flow continues as our journey through the hidden world of groundwater comes to a close. Take a deep breath. Imagine the earth beneath you not empty, but full of quiet motion, full of ancient memory, full of cool, slow-moving water that has flowed through the planet's body for millions of years. It has no rush, no noise, no need for attention. Yet it supports forests, feeds rivers, and quenches the thirst of entire civilizations. It sustains life in places where no sunlight reaches. It nourishes roots, life, and wonder. In a world of constant noise, this water is a lesson in stillness. Let that stillness cradle your thoughts tonight. Let your mind, like groundwater, slow its pace, drift deep, flow softly, settle into layers of rest, like rain seeping into the earth, just as aquifers lie quietly beneath us. Your own calm waits beneath the surface of your day. You need not search for it. It is already there. So tonight, as you close your eyes, imagine cool water moving gently below the surface. Imagine the slow breathing of the planet. Imagine peace so deep it touches stone, and let sleep come like that quiet flow steadily, invisibly, without effort. You are safe. You are held. The earth is humming beneath you. Good night. From the world below, sleep well.